Sounds good.
So radiometric dating, we kind of talked via email, and I sent you the sources that I was planning on using, at least for our talk today, and kind of what I've got in my PowerPoint. I have a couple of others, but I almost sent them to you this morning, but I was like, I'm using them for like a blurb that's on the screen, so I figured it wouldn't be super helpful. But if you want them, I can always send them to you after this, and you can tell me what you think.
Sure.
Or we can go on from there.
Cool.
So the way I kind of figured that this would go based off of our emails is I've got a PowerPoint. It's a beefy PowerPoint. And I figured we would just kind of go through it together. And like
let's do it.
Stop and dialogue, like when we felt it was a good time to stop and dialogue. Great. It's basically structured like I start with, is radiometric dating a good natural clock? What other ways can we kind of support radiometric dating? And then kind of lastly, I was like, then this is like the last third of the presentation is, how does this apply to fossils, right? How do we use radiometric dating to date our fossils? So here's it's not aesthetically pleasing. I will warn you ahead of time.
Okay, no problem.
And I can't see you from where I'm presenting from, so it's like, just holler if you want me to stop.
Sounds good.
Interrupt me. So radiometric dating. What makes a good natural clock? This is something that the Bible Rocks in Time, which is my primary reference for this kind of talk, really hammers home, right? In order to use a good natural clock, whatever you're using has to have known initial conditions. It has to have constant or relatively constant rates. So if it's not constant, it has to be changing in a predictable way that is diagnosable. It needs to be irreversible, and it has to have known final conditions, right? This is basically just pretty intuitive, I think, because if you don't know what it is at the beginning, and if you don't know what it is at the end, how can you actually use it to mark time? And if the hand on the clock is ticking at different rates when it passes the 1 versus when it passes the 4, that can throw you off too, right? And if the clock is ticking backwards, obviously that's not good either. So can we show that radiometric dating is a good natural clock? I do believe that we can. So you already know this, but since we're recording this, and if we do end up kind of posting it, I kind of want to go over this just for the sake of folks at home. Like, how does radiometric dating work? Well, radiometric dating works on the basis of what's called the radioactive decay law in physics, which basically just states that some atoms of a particular chemical element are going to spontaneously decay into atoms of another particular chemical element. And this decay should be constant, right? In radioactive material, which is what we use for radiometric dating, right? Like we pull up a rock sample, we analyze it for its content using usually some kind of spectroscopy, and then we analyze that radioactive material. And in that radioactive material, those unstable elements are the ones that are decaying into stable elements at these specific rates. So in relation to this first statement, it's some atoms of unstable elements will spontaneously decay into elements of stable elements, or isotopes, or atoms of stable isotopes, And that rate's going to be measured in what's called a half-life. So every half-life, half of the material has decayed into daughter material. And all that basically means is that when we take a sample of rock, the ratio of parent to daughter material, if we know the decay constant, should be able to tell us how old the rock is, assuming that it meets this criteria for a good natural clock. So all of that is assumptions. Can we actually meet the assumptions? This relationship is shown mathematically like this. This is pretty similar to most of the stuff that you're going to see in physics, where it's like T equals time, D is the daughter product that we measure today, P is the number of atoms in the parent isotope today. We take the natural log of 1 plus that, and then that lambda is our appropriate decay constant, because the decay constant changes depending on the unstable element that we're looking at. And then finding the decay constant for a parent isotope is in that little equation at the bottom. So can we show that it has old daughter material at the end? Do we know the final conditions of radiometric dating? And yes, this is a pretty easy one to show because we observe it today all the time. There are just hundreds, if not thousands, of isotopes, radioactive nuclides, that have very short half-lives. Some, like carbon-14, have half-lives that are like 5,700 years, but some have half-lives that are in the seconds or picoseconds even. And we've never seen a final product, right, where all the parent material has decayed, where it isn't all daughter material. It doesn't turn into something else. It's all daughter material. So that's our first assumption met. But do we know that we start with all parent material? I have two lines of kind of reasoning here, and the first is that we observe igneous rocks, which is typically what's used for radiometric dating, and if it's not being if igneous rocks aren't being used, it will say, or it should say, but igneous rocks form today, right? Mount St. Helens, Hawaii, all of these show no high strontium ratios. So when we date these older rocks, we usually use, it's a bit outdated today, but it's good for isochron still, a ratio called rubidium strontium. So the parent is rubidium, it's decaying into strontium, and when we measure these new rocks that are forming, they're all rubidium, always. They're all parent material. And we can observe this, like I said, at Mount St. Helens, Hawaii, and in basalt magmas today. But with that being said, it does become inconsequential when we consider isochron dating, which is this type of radiometric dating that doesn't make any assumptions about the parent material in the sample. And isochron dating, we won't get super into it because it's really, really boring to me, sorry geologists. But it works like this. You take a bunch of different samples of a given rock, and you don't just measure the parent to the daughter, you measure the parent to the daughter, or rather the parent to a stable version of the daughter, as well as the daughter to the stable version of the daughter. So over here with the rubidium strontium, rubidium-87 is the unstable element. So rubidium-87 decays into strontium-87, but strontium-86 is really stable. It stays constant throughout the rock and doesn't turn into anything else. So by taking the ratio of the unstable over the stable versus the parent over the stable, you can work backwards with your present condition and find out how much parent material you had in the first place. And as I hope to show later in some sources and some kind of conversations that we should have, it is almost always, I couldn't find an example of not being 100% parent at formation. So, okay, what about radiometric decay? Is it reversible? This is kind of inconsequential again to the young Earth creationism conversation, given readings that we have today tend to be very old in radiometric dating, so reversibility would only add time to that. But it's worth noting regardless that irreversibility being a good criteria of a natural clock, this is something radiometric decay fits. We don't know that of any example, at least that I could find, and when I asked other kind of geologists and physics guys about this, no one could give me any kind of example of radiometric decay going backwards, unless you were literally reversing time, which I mean everything is reversible if you can reverse time. So at present, radiometric decay checks 3 boxes. We know that we can trust radiometric decay in that we can test for initial known conditions, and we know the final condition is all daughter material. We also know that it's irreversible in that over the course of our observation and through our testing, we have not been able to reverse it. But here's the big one. Are radiometric decay rates constant? Because this would have an enormous implication on dating fossils, right? If the decay rates are changing all over the place, you can't trust a single date. Now, accelerating decay, so speeding it up, would be a huge deal for the energy industry, right? They would be able to do a whole lot of work within nuclear physics that would be quite helpful. So physicists have, through time, ever since the splitting of the atom, attempted to speed up decay by several radioisotopes, by several means, right? I also got this from the Bible Rocks in Time, by Yearly and Stern, I believe. We've tried extremely high and low pressures and temperatures. We've bombarded them with high energy particles. We've irradiated them with X-rays and gamma rays, and we've put electrical and magnetic fields to them of varying intensity, as well as accelerating gravity. I don't have any idea how they did that last one, but evidently they did. And the change they were able to get was typically around 0.1%. So radiometric decay in this case is working a lot like time does. It can kind of change, but only under these very, very extreme conditions that are not going to be found on Earth. But how do we know half-lives, right? Because half-lives are a critical part of that equation from the beginning. So I've put a half-life list here and cited, this was actually from the Bible Rocks in Time. I just put it here for the benefit of folks out there who might be watching if we do indeed post this. But half-lives of super old elements, like this rubidium strontium down at the bottom, okay, even in conventional secular science, right, like the universe isn't 49 billion years old. So how do we know that's the half-life if we haven't observed a half-life actually elapsing? And the answer to that is half-lives of very old material, according to the National Nuclear Data Center, are observed disintegrating through their first half-life. So it's not like one half-life passes and spontaneously all those elements decay. It's more like over that first half-life, they're decaying very slowly. So we can see them in the process, even if a half-life has not elapsed. Okay, cool. Now, I put this in here just because this was something that I thought was interesting with kind of the young Earth creationism side of things. Young Earth creationists had this group called the RATE team, which stands for Radioisotopes in the Age of the Earth. And they basically discontinued in 2005. But one thing that they did note is that you really can't speed up decay in any way that they could find, at least in their studies. They said a young Earth position can't be reconciled with the scientific data without assuming exotic solutions will be discovered in the future. This is just in reference to speeding up that decay. They say no known thermodynamic process can account for the heat removal. That's kind of unimportant to our point here. But more importantly, that radiation damage of speeding up decay is tough to cope with. Not important to our point. I mostly was just including it because I thought it was interesting that, they don't tend to be big fans of the constant decay rate, but the RATE team nonetheless was quite honest in their findings there. So, okay, radiometric dating does have the criteria for being a good natural clock, at least as far as we've gotten so far. So we know the initial known conditions. We have tests that can kind of look at that through Isochron, but we also observe that it's all parent material in new rocks that form today in volcanic areas. We know that the rates are constant, especially in nature. We know that they're irreversible because it's never been seen reversing. It's a law in physics. It's very difficult to fight that kind of entropic decay. And we know that they have final known conditions because we've seen hundreds of thousands of very short-lived radioisotopes finish their decay. Okay, fine. So what else can we say about radiometric dating? Radiometric dating is really important to the energy industry. I've included here a recent paper that's on the petroleum and mineral industries. So basically they found a new way of radioactive decay, or new way of radioactive dating, radiometric dating, the rhenium-osmium system, which is neat because we typically didn't use that before. Usually it's like argon-argon or, rubidium, strontium, these kind of classic types. But they were like, nope, we found a new way to do it, and it's really good because it can help us find the time of oil generation and aid us in kind of obtaining these natural resources. And I included this as well. This was from one of my geologist friends who linked me this paper from 2009, which talks about how radiometric dating is used to basin model pretty much anywhere that you're going to dig for oil or coal or natural gas. A quote from this paper that I've included here is on this page. Again, that's Al-Hajiri, 2009, where they say the absolute age of each layer in the basin and petroleum system model is an important parameter for determining the timing of the processes that generate, move, and trap petroleum. Age information may be available from the paleontologic data, radiometric dating, fission track dates, and magnetic reversal tracking. In many basins, known petroleum rock sources have been assigned to global geologic positions based on geochemical and biostratigraphic determinations. So they do use radiometric dating to help us find oil and gas. And this is a second example of that from, let's see. Oh, I don't have the author here. That's bad practice. But what they say is basin modeling requires, first of all, a well-designed geologic time framework, and they discuss how that's kind of important before you actually start drilling, because it would be a huge waste of money to just say, okay, here looks good, and then they stick the pipe down there and start trying to pump, but really they're in solid rock. It's helpful to try and model an area to find out if it's good for oil formation. And to find out if it's good for oil formation, they usually radiometrically date it because some areas, some geologic periods are more well known for oil than others are. So what about discordant dates? I sent this to you already, Rebekah, but for those of you out there, I really liked this. This is also from the Bible Rocks in Time. And what this effectively notes is that when you sample several different rocks and you get slightly different dates using different methods, technically that's a discordant date. But like Yearly and Stern noted here, if you took a bunch of samples from the ISAC gneiss complex, and you dated them using lead, uranium, lead, and rubidium, strontium, and you got 3.6 to 3.7 billion years, and then you tried samarium and didymium, and you got 3.74 billion years, and then you did lead, and samarium and didymium again, and you got 3.7 to 3.81. You would get the feeling generally, as on and on, that this thing is around 3.75 billion years old. But that being said, technically those are discordant dates. They still converge on a general idea, though, which is why ranges are so important. Okay, so we've established that, at least according to conventional methods, radiometric dating is a good natural clock, and we've established that it is useful to us economically, right? We use it to find the energy that, I'm in a house right now that's obviously being fueled by, coal, effectively. So I'm warm and toasty because of the processes through basin modeling and radiometric dating that have led to the discovery of things like coal. But how does radiometric dating square with other dating methods? This is really, really important in my opinion, because radiometric dating, theoretically, if it didn't work, it could not work in kind of a stepwise way, right? That had something to do with an impact that some random thing maybe had on the process of decay itself. The reason comparing it to other dating methods is good is because these are all independent to radioactive decay, right? Tree rings, varves, ice cores, continental drift, and especially human historical records have nothing to do with the rate of decay when it comes to like radiometric dating, right? Tree rings, you just count them. So I thought I would do a little thing here and compare it to 5 relatively quick kind of historical methods. So I sent this one to Rebekah. I really like this one, radiometric dating and Mount Vesuvius, right? So we have historical records from Pliny the Elder, who was like, oh my gosh, there's been a horrible disaster. Pompeii and Herculaneum are not there anymore. Mount Vesuvius erupted and destroyed them completely. And this happened in, I think, 79 AD. So back in, this was 2007, right? But there's another 1998 paper that does a really good job with this. They were like, okay, let's argon date the material and see what we get. And as you can see from the abstract here, and also from the one that I sent Rebekah, that was Wren et al. 1997, I believe. They got it to the calendar year of 79 AD. So that's really interesting. Why is it that we can track our human historical records back to 79 AD, and then also radiometric dating converges on that date? Tree rings, this is another really interesting one. So you can count tree rings. Tree rings tend to add 1 ring every year. Some years they'll add 2, some years they'll add none. It's actually more common for them to add no rings during the year than more than 1 ring, just because it's how the tree's biology works, right? Like they decide not to waste energy on growth and instead use that energy on maintaining. Whereas when they have extra energy, they usually put that into expanding branches rather than growing outwards. But the cool thing about tree rings is that you can create a sequence, right? If you have 1 log, right, today, that's of a still living tree, you say you cut down a tree in your backyard, you might find 1 ring in there that's characteristic from, like, let's call it the drought of 1909. There's a horrific drought. You can take that ring's characteristics and match it to an even older tree, right? Because the trees are going to respond in relatively the same way to a severe drought and mark that event in their rings. And through that, you can actually count back tree rings through a sequence, right? From taking it from log cabins to taking it from ancient forests. And you can kind of count them and get an uninterrupted sequence. And Ken Wolgemuth talked about this on my channel as well for quite some time. He's a cool dude. He's actually an old Earth creationist. So we disagree on evolution, but we do agree on the age of the Earth. So you can take that sequence back about 14,000 years through this series of oak tree forests in Germany, which is fascinating. That's really interesting. But this makes for a nice corroboration for radiometric dating because we can also radiometrically date these trees because they're younger than 50,000 years. So over here on the right is a plot that Ken actually drew up. He's a retired petroleum geologist these days. And in purple are the 2 lines that exist for the range of carbon-14, right? Because carbon-14 can alter in the atmosphere, but not by much unless you're doing what we're doing today, which is adding a lot of extra very, very quickly. But in the past, things stay relatively constant. So here was our guesstimate in these two purple lines of the range for what we should see if we carbon-14 dated organic material. And then the red is the tree ring dates. And what you see is that the tree ring dates, by counting, match precisely with the carbon-14 dated year, which is really interesting. Obviously, there's variation in there, right? But it fits snugly within those expectations created by radiometric dating. And it works for the Dead Sea Scrolls as well. Ken Wolgemuth is a Christian, and he actually put this in here because he thought it was super interesting, right? You can actually put the Dead Sea Scrolls in here, and lo and behold, it lands perfectly not only within the carbon-14 dating range, but smack dab on the tree ring range too, on the tree ring line as well, at 2100 years or 100 BC. Here's the official published chart. It's the Heidelberg tree rings. That's that German sequence I was just talking about. And I can link this to you if you'd like, but I kind of put this in last minute because I was like, I trust Ken, but I wanted to put this in here as well, just so you know that there was a real study on it, which is neat. Sorry, cool. I'm monologuing pretty fast. Let me know if you want me to stop or anything.
No, you're great. You're doing a great job.
Okay, just stop me if you need me to. Okay, cool. But what about other methods? So we've looked at historical records and we've looked at carbon dating. What about varves? So varves, for those of you maybe out in the audience who don't know, are lake deposits. They're deposits of sediment, right? And a varve is specifically a kind of sediment that is related to some kind of cyclic cycle. So over here on the left is just regular old sediments, right? There's no pattern to it. Over here on the right, though, we see a banding of light and dark. And it turns out if you actually go in and look at those bandings, you'll find that they have a different chemical composition, and that it's related to things like pollen or algae blooms, which suggests, at least according to what we see observing today on how pollen and algae behaves, it blooms in the summer and it goes away in the winter. It turns out that it was the same way in the past. Ancient lakes that were near, big forests have pollen-saturated summer bands, summer varves, and relatively dead winter varves, because lakes don't stop depositing sediment in the winter. They just kind of keep going. So we have this nice banding pattern. Okay, cool. So why does that matter? Because you can count varves, right? You can say one summer varve plus one winter varve equals 1 year, which is typically how varves function. And the cool thing is the varves can also overlay with the tree ring data and the carbon dating, which is what, again, Ken did this, not me. This is from my talk with him, and I'll link that to you if you want to watch it, because he knows this stuff. They also overlap and fall within that carbon-14 dating curve. And specifically, if you zoom in, so this, just so you know, is zoomed in on this little section right here where the two converge, because tree ring data goes back only so far, and varves go back significantly further. And it turns out that not only do they converge generally, but they can converge on a calendar year from 11,240. So this is that nice plot. I thought that was really cool. I mean, Ken did this all himself. So we have three methods so far that have converged two methods that have corroborated and converged on a specific kind of radiometric dating, carbon dating, as well as Pliny the Elder's work corroborating argon dating. Ice cores, though, help us as well. So Iceland's covered in volcanoes, right? And these volcanoes kind of erupt at random intervals. Like, we can't predict them very well, even today with all our modern technology. But every year also, it snows in Iceland. So the snow falls down, and if there happens to be a volcanic eruption at the same time, sorry, I've got a dog. If there happens to be a volcanic eruption at the same time, that ash ends up falling in with the snow. And the cool thing about ash is that it doesn't just contain, like what we typically think of as ash, like that soft material, sediment. But it also contains very small igneous rocks that can themselves be dated. So what Ken is showing here is the fact that you can count ice cores, right? It's yearly snows through ice cores, as you can kind of see in this picture here. You can actually see banding within ice cores, right? And you can count those bandings for each calendar year, and they match up with radiometric dates that we get for certain ashes within these ice cores. Okay, you might think, so what? But you can take those ash from those ice cores and compare it to local Iceland volcanoes and actually corroborate which volcano erupted when, just using the volcanic dates, the radiometric dates of the ash in the ice cores and the new igneous rock that's found in these volcanoes, which is kind of neat as well. But the big one for me, and I talked to Rebekah very, very briefly, but I was super sick, so I probably butchered it once before, is Continental Drift. So what's over here on the right is what's called the Mid-Atlantic Ridge. And the Mid-Atlantic Ridge is a spot that kind of separates our sort of new world, quote unquote, from the old world. And it's a spot in the middle of the ocean where continental plates are pulling apart, right? So magma wells up at this big fault line down the middle. And when that magma comes up to the surface, it cools, right? And once it starts to cool, as we know from how igneous rocks behave, that's when the radiometric clock starts ticking. But because magma keeps welling up and the plates keep pulling apart, magma that is newly on the ridge, as the years pass, will be pushed, or pulled rather, further away from the Mid-Atlantic Ridge. So this creates a really interesting test for radiometric dating, because we can take samples from certain distances away from the Mid-Atlantic Ridge and radiometrically date them, to see how old the decay says that this rock is. And we can collaborate that. We can cross that with the rate at which we should see the continents pulling apart based off of the current rate that the continents are moving apart today, which is about 1.2 inches per year. And if you do that, this was actually done by Joel Duff, he runs the Natural Historia blog. He's also a Christian, but I think he's a theistic evolutionist. Ken is OEC. And you get a plot that looks like this. And he did this, I think, from his work over in Jordan. But what you get is over on the y-axis is estimates of the rates based off of like geologic slips. So on the y-axis, we're looking at continental plates moving away from one another. And on the x-axis, we're looking at dates that we should see from radiometric dating, right? And if you plot y versus x, you should see the line, right? The dots that we actually sample should fall along the line. So the line is the prediction, and the dots are the data points themselves. And what do? Well, radiometric dating converges on the same rate as continental drift, and they plot along the line, which is to say these two things are effectively in lockstep with one another, which is what we would expect if radiometric dating can indeed be trusted. So that's like 2/3 through the presentation. We're so close. But now I wanted to bring up how does this work with fossils, right? How does this matter for human evolution, which is the thing that I really want to actually talk about. And it's very relevant. So most fossils cannot be dated directly. Anybody who tells you that most fossils are dated directly is just wrong. Most of the time, you can't date them directly. And the reason is because fossils tend to not be the original bone unless they're very recent. Usually what happens is a fossil is preserved, and then as it's kind of preserved, it permineralizes. So it's replaced slowly over time with rock. But because it's slowly over time, you can't date that rock and expect to get a consistent date. It's not usually igneous rock, right? If magma came over the fossil and replaced it, the fossil would just be instantly destroyed and you wouldn't get anything except for a block of magma. So it usually is sedimentary or metamorphic rock, which cannot be dated easily. So, like I said, fossils are usually found in sedimentary rock, so a thing dies and it's covered with, let's say maybe a mudslide gets them, or they fall into a eutrophic lake, or, regular natural processes kind of scatter the bones around and regular wind sedimentation covers them up. It doesn't really matter. Usually they're not in rock in rock that is directly datable, and they themselves are not directly datable. So this is common in human evolution. Right? We can't date the fossil itself, and we can't really even date, usually, the direct rock that it's in. So what do? How do we solve this problem? Well, in human evolution, we usually date fossils by their position in relation to datable layers, rather than them themselves. And usually this involves a massive taphonomic study to be sure that the rock itself hasn't been reworked. And there's quite a bit of work that's been done by geologists on how to tell chemically if rock has been reworked as well as mechanically. So the step one is to make sure that, this thing is in the original rock it was buried in. And then step two is to look at where it is relative to actually rocks that are datable. So the most common way we do it in human evolution is using volcanic tuffs. I wrote tufts here. I think that was a autocorrect issue. It should be TUFF. And formally, this is called tephrochronology, which is literally just radiometrically dating those small igneous rocks that are found within volcanic ash. And people usually don't understand like how intense volcanic eruptions are because they're rare and they don't really happen here in the United States or in most places that are kind of settled. But here at the top over here where it says dust on the card, this is a picture after the Mount St. Helens eruption. And dust from Mount St. Helens ash made it as far as Oklahoma. So that ash travels pretty far. So basically in Africa, which is where humans are proposed to have evolved, ash, anytime any volcano erupts, even in the general vicinity, you're going to get a nice datable ash layer. And then I showed a picture of a volcano erupting. And this is kind of how it looks, right? For this reason, human evolution dates are almost always a range because you're showing the minimum, which is the datable layer below the fossil, and the maximum, which is the datable layer above the fossil, right? So this right here, little bone is shown, and we see zircon fission track dating material above and below. So we know that whatever this bone is, it was laid down some point between 0.88 plus or minus 0.07 million years ago and 0.8 plus or minus 0.07 million years ago. And that's usually how these fossils are dated. So how does that hash out in the literature? And I included this chart as well just because sometimes if you can in human evolution, at least in the fossil specimens that I've presented here, as well as the ones that you typically see in the literature, they try to do more than one. So you're not going to just uranium lead date a layer above and below, like in this situation. You're going to uranium date it, and then you're going to see if you can do maybe magnetostratigraphy as well, or specifically fission tracks, or uranium lead series, or sorry, I said that first time, potassium argon dating, whatever. You want to do as many as possible because as we showed earlier, if all is well, multiple dating methods should converge. So, I'll start off this little section by saying I'm not covering some of the earliest hominins, which includes Sahelanthropus chilensis 7 million years ago, Auroran-tuganensis 6.1 to 5.7 million years ago, and Artypithecus cadaba 5.7 to 5.2. And the reason is because I didn't think they were very important for the conversation. They're cool fossils, but I just didn't include them. We're starting with Artypitheceramidus, which is actually my favorite fossil. And this over to the right is the report of the holotype. So when it was very first discovered and reported on by Tim White, you get the horizon and associations down here in red, which says all hominid specimens were surface finds located in the section within 3 meters of the Da'am A2 basaltic tuft. The immediately underlying Gaala vitric tuft complex is at 4.39 plus or minus 0.03 million years ago. So by running a geologic test, right, by actually radiometric dating these tufts, you can get a decent range for when the organism lived, assuming that it's not reworked, which is why you get things like this, ecological and temporal placement of early Pliocene hominids, which is entire studies that are dedicated just to examining the nature of the strata that the hominid or whatever, maybe you're looking at dinosaurs even further back in time, entire studies dedicated just to that single site to make sure that your radioisotopic dates are matching with general geochronology and any other method that you can run. And this is Artypitheceramidus. I'm including the fossils just because I think they're cool. This is what it looks like on that chart I sent you. And here's where it falls, right? 4.4 million years ago. Or rather 3.9 plus or minus, I think 4.39, plus or minus 0.03 million years ago. That's a nice tight date. Not all of them are like this. So we've got a nice date for this. Okay, cool. We're not talking about the morphology or anything. We're just talking about dating fossils. Next is Australopithecus afarensis. This is the same species as Lucy. I'm skipping a lot of species here. I'm just picking a couple that I liked. And here are two papers, one from Leakey. These are two different specimens in two different papers. One that was dated to 3.5 million years ago with between these two tufts, right? The Tulu boar and the Lomekwi member. And then below, we're talking about a different specimen that, again, is between to tufts. I'm not going to bore you by reading all of them. I'm just showing that every time a fossil is discovered, you can't really talk very much about it unless you get geologists out there to actually show that the dates are legit. Usually they'll go out there, they'll pull up a fossil and they'll say, okay, like based off of what I know about the area, it's probably between, 1 and 2 million years ago, but that's not good enough. You want to narrow it down, which is why pretty much every anthropologic, paleoanthropologic team has a set of geologists who come out there and do radiometric dating and geochronology on it. So that's some specimens of Australopithecus afarensis. It's important to note that there are a lot of them, right? We have several specimens of most hominins. There are exceptions, of course. Sahelanthropus, there's only one of those, and it's from 7 million years ago, right? But most of these guys, especially Australopithecines, we've got a lot of them, and they all have to be radiometrically dated. And what we find is that once you take into account the dates of all of them, you get a 3.2 to 2.9 million year range, which is not for any one specimen, but rather for all specimens taken into account. The very youngest we have and the very oldest creates that range. So Australopithecus africanus, I like this one because it didn't just use radiometric dating, it also used paleomagnetism. And the way that works is every time the magnetic field of Earth reverses, you can find traces of it if iron is in the sediment, because the polarity will switch. So they used both of those to look at Sterkfontein, I was thinking Swartkrons, it's in different areas, the Sterkfontein paleocave deposits, in order to tell how old these Australopithecus africanus specimens are. That's Australopithecus africanus. And the range when you take into account all of the specimens of Australopithecus africanus is 3 to 2 million years ago. Really wide range. We find these guys all over the place. They did the same with Australopithecus Sediba. I included a nice picture from this paper over here, Geologic Setting and Age of Australopithecus Sediba. And this one they used flowstones and tufts, I think, and paleomagnetism. So 3 different methods. And they got a range of 1.95 to 1.78 for the lower level, or for the older area, the older facies, excuse me. And that's kind of, again, the picture of the different facies. I think I'm butchering this because they've got 2.36 to 1.5. Okay, I'm so sorry. The second thing I said was the upper layer, and then 2.026 plus or minus 0.021 million years ago. Okay, got it. That's the upper, that's the lower, and this is the upper. So you end up, this is the specimen, by the way. It was a juvenile male and an adult female, MH1 and MH2 from the Malapasite. And it's an interesting find. Okay, cool, there it is. And here's where it falls. Note, there is overlap. A lot of these hominins have periods where they're contemporaneous. This is not unexpected unless you're taking the 1800s idea of evolution where everything is anagenetic, or the second a species evolves into something else, the previous version of it dies out. No one I know really accepts that, except maybe Tim White for Artypithecus. Anyways, so Homo habilis is next on the list. They used argon dating of tuffs and lavas, again from this, from the Olduvai Gorge Bed 1. So this is the chronology of that from the Pleistocene. Here it is over here in F. Here's where it falls in blue. So it's overlapping heavily with Australopithecus africanus, but it's not found in South Africa. It's found in East Africa. So if you take out this red bar of Australopithecus africanus, you see a very interesting, what looks like, quote unquote, a transition between Australopithecus afarensis and Homo habilis. So what's this middle guy, Africanus, doing? Well, I don't know. Some people think that Australopithecus afarensis, which of course shows up much earlier than any of our specimens of Africanus right now, had a split off that moved down into South Africa and continued to live there, while some members stayed in East Africa and eventually underwent some kind of pressure that favored larger brain sizes and, I guess, even more efficient bipedality. That's all speculation for right now. Homo rudolfensis, same thing. They looked at the Moiety tuft and the Malbay tuft, as well as the Silbo tuft and the Chari tuft, and they get a range for this guy of 2 million years, which is not very much. Effectively, we don't have very much material from Homo rudolfensis. We've got like a couple really good skulls, but they all seem to hone in on this 2 million year range. Why that is, I have no idea. Maybe they just really thrived during that period. Homo ergaster and / Homo erectus. This is mostly because some people think that ergaster should be Homo erectus. They're very similar. There's a lot of overlap in morphology. But here's a characteristic skull, and here's how they did the magnetostratigraphy for Olduvai Gorge again, as well as Cubiphora writ large. And the way that they did this was through radioisotopic dating. I think it was uranium-lead. But I didn't include as much of the abstract as I wanted, or as much of the paper as I wanted, so apologies for that. I thought I included more of it. So there's J. Homo erectus' range is insane. This thing lived for a very, very long time, and we find it not just in Africa, but all over Eurasia. This thing is just very, very ubiquitous. But the oldest material is Africa and pretty close, so, it looks like that's where it got its start. And then Homo sapiens, of course, the oldest Homo sapiens skulls, physical material we have, are Epidema 1 from the Epidema cave site. And these guys, for this one, they used, let me see here, uranium series radiometric dating methods. There's archaic Homo sapiens. It's from about 300,000 years ago. And then that's the range for Homo sapiens, our species, as far as we know it. 300,000 years ago, with this individual being perhaps one of the oldest. To present. So what I want to be appreciated here is that a lot of these hominins have ranges, right? But the ranges of the most basal ones overlap very little with the beginnings of the more derived versions as you continue through geologic time. We never find Homo erectus earlier than Artypithecus. We don't find Homo sapiens earlier than Australopithecus, right? We see a procession, and while there, of course, is contemporaneity, right, which it used a long time ago, people didn't expect that. Again, they thought it was very anagenetic, but not so. Things kind of trail and continue onward, right? It's kind of like wolves didn't go extinct because we domesticated dogs, right? They're still around, they're still thriving. And then I thought this was quite nice as well, a more official-looking chart that charts just how big the brain case gets through time of all hominins, from the ones that we think are directly related to humans, from the ones that aren't. That would be these paranthropines here. And what we see is a steady increase, so morphologic change through geologic time. And that's all I got. So what I was hoping, kind of, I guess, I know that was like a lot, but what I was kind of hoping to illustrate was this nature of like, okay, what's radiometric dating? Can we trust it? Does it make a good natural clock? How do we use it? And then how does it apply to fossils? How do you feel about that?
Well, I think you did a good overview. I guess there's a couple questions that come up in my mind related to the fossils. And that is, I'm glad you showed kind of some of the pictures, like the physical photographs of the sites. But, when I'm looking at the chart, I would like to, you were just doing it very quickly on slides, so it's hard to kind of look at the details. No, you're a great teacher. And so that was really good. But I would like to slow down and really look at each fossil. What do we have of the fossil? Where was that found? Was it found together? Was it found apart? And the various layers, you mentioned one dating method was used here, in some cases. And so I'd like to understand, why did they use that particular dating method? Because in the stuff that you sent me about the dating methods, there were admissions that, hey, sometimes, it does give discordant dates. And so, there is a range. And so, and some of the dating has turned out not to be as reliable as they hoped, like the rubidium, strontium. And so, and then in one case it said, we can't safely make assumptions about the daughter element in some cases. So, and that's in the stuff you sent me, not anything, that I looked up separately. Yeah. So, and so with a lot of admissions about the difficulty of trying to pin down the conditions, the effects, and especially if we're talking about millions of years, the difficulty of trying to discover what has actually happened to these rocks in that time period, even though I don't accept those, time periods. But for the sake of our talk, just in case we are putting this out, we have agreed that I'm granting the age of the Earth for the purpose of these talks, even though I am a young Earth creationist. But it's a matter of I don't know that I've been given reliable reasons, although I will say your presentation about the rings, the tree rings, the ice cores, and the varves, that was really excellent. I like how there's a corresponding. I have to say that was very excellent.
I wish I could take credit for it. That's all Ken. I mean, Ken is the one who presented that to me. He's the one who did the legwork for it. So I'm going to link his video if we do post this, but I'll send it to you. I think the video is just called Creation Story on my channel. You should find it's like a video in Grand Canyon. I think you raise good questions. I think that's all fair to ask. I mean, how do we know the conditions of rocks, right? And how does this impact interpretations of certain fossil sites? Because you're absolutely right. Sometimes these things change. I will say that I've never seen a change in a fossil site that is more than maybe 1/10 of a million years. Usually it's 100,000 years. And what I was hoping to show kind of at the end is that, human evolution kind of makes a relatively simple prediction, right? It's okay, we should see the ratio of traits, right? So what makes us human and separates us from, this idea of this basal ape living in the Miocene, or, for reference, say maybe something like a chimpanzee. We should see the emergence of the human-looking traits in organisms and the loss of those more primitive-looking traits through geologic time. And once they arrive, they should probably stick around. At least the big ones should, right? Big brains, walking on 2 feet. And what I was kind of hoping to show, at least with some of those charts at the end with these big overlapping bars, is that, we do seem to see, while there's absolutely these ranges, and the distal ends of those ranges might change, or let's say we found a member of Lucy's species, Australopithecus Africanus, much earlier, right? That bar would extend, and maybe it would swallow up Artypitheceramidus's bar, and if we're proposing that Lucy is the common ancestor, eliminate Artypitheceramidus from being on our lineage. It would boot it to the side. But even if that does happen, which it could, I mean, I don't know what's going to happen tomorrow, it wouldn't change the fact that we see the basal to the derived, and those radiometric dates, while they're subject to change, it would violate precedents in a very serious way for it to change so much that we would have something like a human removed by 4 million years. You know what I mean?
Yeah, I would agree that would be strange. What I'm wondering, though, is how accurate, and I have not looked into this volcanic tuffs thing at all, but just initially, my initial response to this being dated by volcanic tuffs is you're showing a layer of ash. But I mean, how can we say that layer of ash is still datable, considering that this has been millions of years and you're talking about a very thin thing in this? I that's just one thing that I'm skeptical about, but I don't have any information about. And so one of the reasons, go ahead.
No, sorry, I interrupted you. Go ahead and finish.
Well, I might be going on to a different point, so go ahead if you want to respond to that.
Yeah, I'll be quick. So the Pompeii stuff, that argon dating, that was dating volcanic ash, right? So the way that you date the ash, right, is that ash is composed in part of really, really small pieces of rock. And that rock is igneous, which is the only kind of rock that you can radiometrically date, period, because we know that if it's igneous in nature, we know that it went from molten and then it hardened, and that's what starts the clock. That cooling activity chemically starts that decay clock, right? So the idea would be that what those thin layers, it doesn't matter how thin they are. It could be as thin, it could be the thinnest possible, literally grain after grain after grain. although I have seen some of these for myself when I went to Olduvai Gorge years ago. Some of them are pretty thick, that thick, that thick. It depends on how severe the volcanic eruption was, and how close it was. That's another thing that's really important. If the volcanic eruption was really close, you're probably going to get, feet and feet of ash like we saw with Mount St. Helens in real time when we observed how volcanic eruptions spread ash around back in the 1980s. But if you live in Oklahoma, while ash did get there, it was not that much. It's like a thin layer of dusting on your car. So it's important to be able to do that, but that's why I included those ice core things, because what happened with those ice cores is those volcanoes are all around Iceland. When they erupt, not only do they spew ash into the air, which is then, compacted and crushed into these ice core layers, which can be radiometrically dated, but they also have regular magma flows, as most volcanoes do. So an ability to check this would be, and we've been able to do this in Africa as well, is to go to these volcanoes, date the igneous rock column, and see if you can find a radiometric date that matches the one from the ash layer. At least that's how they did it in Iceland, and that's how we've done it in East Africa as well. So what that says is that, okay, it looks like the ash that we have did indeed come from this volcano. And that's at least my understanding of how it works.
Okay, well, something that would be interesting to me and would be kind of like confirming evidence is, the Mount Vesuvius eruption was, the tuff was dated with radiocarbon dating, right?
Argon.
Oh, argon, sorry. Mm-hmm. But what would be interesting to me is to see, those type of things dated with the rock layers or the volcanic tuff that the fossils are found in. Just simply because I'm suspicious. Okay, I'm suspicious simply because I hear all these things about the dates, and of course in the young Earth creation community, there's a lot of talk about how when you go submit a rock sample, they ask you for what you think is the estimated date. Mm-hmm. Now, I don't know if that's true. I can't verify that. I've never submitted a rock sample myself. But that does seem like a suspicious practice if that's what's done. And it seems like is there something going on with that with the geologists that come out and, working with the anthropologists? So those are the kind of things that I get very suspicious about. And I don't just take it for granted that people are being, honest or diligent in the way that they are testing these things, because there is a great desire to find certain discoveries. There's a great desire to make your name known. And so I'm not attributing dishonesty to all scientists or anything like that. I'm just saying that if you're a person who believes very strongly that you have found a human ancestor and you think it's a certain age, then how does that influence your work? And so what I'm looking for is dates that could be trusted. I don't want to know, it was found in this geologic layer, and we know that geologic layer is such and such million years old, so we don't even need to bother to test it. And so for each fossil that is found, I would like to see the hard dates that were done, multiple dating methods used? How did those correspond to each other and that kind of thing? Which that information might have been in the papers that you pulled up.
Yeah, I know that they are. I can send them to you, or I can just give you this file and or I can give you the PowerPoint. You can just Google the names and the paper should come up. But I think I understand. So I understand where you're coming from a point of skepticism, right? So if you're someone, you're like, I don't buy evolution, I think it's, it doesn't work or whatever, you're just skeptical of it, the reasons don't matter. I can understand why you would see motivation there, and I think there is motivation for any scientist, period, who wants to, every scientist wants to discover the next big thing, whether you're working in genetics or geology or anthropology. I think that's just the nature of, I think that's human nature, right? You want to be known for a cool thing. You can't date the rocks that the fossils are found in any case that I know of. And the reason is because it's always sedimentary. This goes for fossils, 10,000 years ago, fossils or bone material that was from like the Mesozoic. That goes for dinosaurs. It goes for things that are found earlier than that, or it goes for fossils that are found relatively recently from a secular standpoint. And the reason is because sedimentary rock is composed of several grains of other rocks, so you don't know which one you're dating. The reason igneous rock is used is for that reason. I find it to be quite honest that these guys are coming out here and they're saying, look, what we can do is we can say, the fossil is here, and half a meter above it is a volcanic layer, and half a meter below it is a volcanic layer. So the range is 2.3 to 1.8 million years, right? That's a lot of time in between them. But I don't think that you need dates down to the calendar day for ancient organisms to show evolution. In fact, I think if you did, you wouldn't really know what you were looking at, because from a secular standpoint, evolution is occurring so slowly that these moments of speciation aren't really. I mean, speciation is a tough concept to cope with in the first place. But it would be looking like two identical organisms with a genetic change that you can't even see, or maybe it's a bump on a bone that would eventually become something significant down the line if it conveys some fitness benefit. So I think it's quite nice that we've got these broad, or not broad ranges per se, but like honest ranges. The ranges get smaller when they can. So for instance, if you have one fossil where it's 2 meters above and 1 meter below, obviously that's a greater date range, because these volcanic layers were deposited at different times. Then if you find one that's half a foot above and half a foot below, for which I believe, if memory serves, there are some that are like that. But I think the most important thing is that take fossils out of it entirely. These volcanic tuffs, which it's just I really want to make this as clear as I can. All volcanic tuffs is very small igneous rocks. So it's the same as normal radiometric dating, but they're just very, very small, right? So ideally you take several samples of any rock, really. If you're doing good science, you should radiometrically date more than one sample at a site. But you're sampling a lot of different, very small rocks rather than, one big rock. That's how radiometric dating of ash works. That's how they did it with the argon dating at Mount Vesuvius, and that's how they do it with other volcanic layers in this case. So I think that if you would want to be, I almost feel like skepticism is healthy, but I feel like suspicion isn't in that case, because I feel like at that point you're basically saying, I don't think there's a way I could show you otherwise. You can't date sedimentary rock. That's not something that you can do. You can date igneous rock, and using isochrons you can date metamorphic rock. But pretty much all fossils are buried in sedimentary rock, unless even when they fall into lakes or tar pits or whatever, you're ultimately using sedimentary rock in relation to dateable materials above or below, because usually if it's dateable, it would destroy the fossil. Hot ash falling directly on a fossil is probably going to destroy it and make it unusable. So I don't think I can show you anything that's would meet your satisfaction if you're at that level of suspicion. What I can show you is that it's like kind of like dirty laundry, right? Like if I wear something last week, it's at the bottom of my laundry basket, and then throughout the day it builds up. I can show you that the layers, much like my clothes, are in appropriate spaces, and that the fossil found between them has not been reworked, which is to say the definitive range is solid, but I can't give you a direct date.
Yeah. Okay, cool. Well, thank you so much. Did you have more that you wanted to share?
Not really. How do you feel about radiometric dating? We could certainly, I feel like I've been doing the young earth creationism thing long enough to know the kind of classic disagreements with radiometric dating.
Right.
And I find most of them, like you mentioned earlier, that you can send a rock sample off and you have to say when you think it was from.
Right.
And this is I actually am glad you brought it up, because it's a very, very critical point. You can't date brand new rock with radiometric dating. Brand new rock will show up like the example that was told to me by a geologist was like, it would be like if you took a microgram scale, that measures percents of grams, and you slapped a semi-truck on it. There's too much parent material, so the clock just goes haywire and breaks. Now, like I said, the second that enough parent material has actually decayed into daughter material to date, like, for instance, Pompeii, 2,000-ish years ago, then you get these pristine calendar dates. But oftentimes, and I'll just speak for myself here, and you can kind of take it or leave it kind of as what I'm saying. But I've tracked down probably over a dozen individual creationists, from Andrew Snelling to Steve Austin, claiming to get these strange dates from sending them into labs. And the rocks that they send in are brand new volcanic rock. They come from Mount St. Helens. They come from the New Zealand basalt. They come from brand new Hawaiian islands. And then they're like, they sent me back a crazy radiometric date when it's brand new. But you can't date brand new rock. I would be interested if they took a sample from, 7 million years ago, right? What is typically 7 million years ago, and told them it was from the Mesozoic, and then saw what happened. Because that would actually be support for their idea that radiometric dating is off if you don't give them this preconception of it. But I have never seen a single example, at least me personally, maybe you have, maybe others have, where the rock that they sent in wasn't brand new. And I feel a bit suspicious, and I'll talk about, mine's not skepticism, I'm suspicious, like conspiracy suspicious, that's intentional, because they know that if they send in rock that's aged enough, they will get the date, whether they tell them the correct date or not, because it's just a ratio of radioactive decay. But by sending in a new rock, they can definitively get a date that doesn't match, because not enough has, and we know this is the case. And that I sent you the radiocarbon thing, but that was specifically on radiocarbon, not which is type of radiometric dating. But isn't radiometric dating like old, like it's not radiometric dating inorganic material, so it would be inapplicable to sending in rocks. But I wasn't super pleased with the rabbit holes that I went down on radiocarbon dating things like dinosaur bones or coal or diamonds, because I'm not a geologist, and I was able to track down with my very rudimentary level of geology understanding issues in methodology, which strikes me as odd for geologists to do, especially because I know Andrew Snelling, a young Earth creationist geologist, for those of you, if we do post this, who don't know, he's a good geologist when he does conventional work. And I don't mean good like I've seen his work and I'm like, I know geology well enough to know that that's good. But he's published in legit journals. But when he publishes in the legit journals, he's doing conventional work, right? Why? And I know maybe there's an element of like suspicion maybe on your side that it's like people who see young Earth material pushed in these journals submitted, they're instantly like, oh, it's young Earth? No, we're not even going to look at it. But I would propose that, at least from my own readings within the tangential geology, but primarily the anthropology stuff, it's because a lot of times very basic protocol isn't followed, and like I said, I'm suspicious that it's because they want the wrong dates. Did I get across kind of what I was saying?
Yeah, but the question that I have is then, if you send in a new rock, shouldn't they test it? Like, if they test it, shouldn't it come up like flat? Like, hey, we can't get a reading on this. Like, should it come back saying millions of years?
It won't say.
So what I'm.
Oh, sorry. Go ahead.
Well, if a new rock comes back saying millions of years, then how can I trust that an old rock that says millions of years is actually millions of years and not also a new rock?
Because it's one of those things where, like, when you're measuring radioactive decay, we usually use AMS, so like it's like a mass spectrometer. Excuse me, that always trips me up. And it's just looking at a ratio of parent to daughter. Right. So in the case of brand new rock, like I'm kind of repeating my earlier analogy, but again, that's how it was explained to me. When there's so much parent and no daughter, it wigs out and just tells you the amount of parent that's effectively in there, which is incredibly ancient, right? Instead of telling you the ratio, which is going to actually give you that correct age, because we know how half-lives work. If this weren't the case, then we shouldn't get things like Mount Vesuvius or the Dead Sea Scrolls, where once enough time has passed, these limits that geologists have for these rocks or organic materials, where they're like, this much has to have decayed or you won't get any kind of accurate reading. Because it's like sticking something that's way too heavy on a scale that's meant to be much more precise. It just blows the whole system up. It shouldn't suddenly stop or start working, after those limits that geologists give. It should either be random or it shouldn't work at all. And yet it's curious that they have this standard and they're like, here's how much for whatever, series you're sending it in for. Because if you're a geologist, you're not saying, I'm sending a rock in, radiometrically date it for me, right? You send in the rock and then they use a certain type of radiometric decay depending on, again, that age that you think it might be. And the reason for that is because you get more, it's not because you can't get general estimate dates, but you get more precise dates if you're using a radiometric dating method that is more, that has a narrower range for these rocks that are more recent than if you would use rubidium strontium has a half-life of 49 billion years on a rock that's 1 million years ago, right? Like, it's going to be really inactive. Those error bars are going to be insane. And, I'll just speak for the carbon dating example, but like some of those carbon dates for the coal that they were submitting in, it's very similar to the kind of problem that, that I was just mentioning, right? Where they're like, look, they found radiocarbon in coal that's supposed to be very ancient. Carbon has this half-life that's very short, 50, 60,000 years. It should be totally gone. Why is there carbon in the coal? And when they do their error bars for it, right, the error bars come back as being like, this rock could be as old as, 80,000 years ago or as new as in 80,000 years. Like, it just shows you how wonky it is when you test something using a method that doesn't work. So you might be thinking, how do we come up with the methods that work? It sure seems convenient that, we've got these methods. And it's by predictions, right? It's making a prediction, like with the Mount Vesuvius example, they were like, okay, we have someone who was there. How rare do we get an opportunity like that? But we have someone who was there, who wrote down when it happened, and the Romans were, meticulous record keepers. So we can actually take their record and say, if argon-argon dating works, this is the year that it should come back with. And lo and behold, it comes back. So you can calibrate, and that's what they did in that 1997 paper and then did again in 2007. You can further calibrate the clock. Back when this was first developed, the error bars were much bigger, but things were still very old. It's like in the Bible Rocks and Time book I gave you, where it's like, right, you get these ranges, but they're all old. They all converge on these very old ages. And in human evolution, this is important because, like, we're getting appropriate ranges. I'd like them to be more precise, but it's not plus or minus 5 million years. It's plus or minus 0.01 in some of those examples that I showed you. So while I think it's okay, like I said, it's okay to be skeptical, I don't think the suspicion is warranted. I think that there's reasons. I think that book that I sent you had a quote in it where the authors were like, none of this is guesswork, right? Like, this was all composed. I mean, when Lyell, the guy who was the first old Earth guy, at least in science, came out and was like, I think the Earth is very ancient. He didn't say it was, 4.8 billion years old, and then we fit everything to mesh that. He was like, it might be 100 million years old, something along those lines. And then it changed as the data came in. And it's still the beauty of science, in my opinion, is that it's mutable and changeable. It's like, we could find out tomorrow, if we found a human fossil 4.4 million years ago, well, that would effectively debunk human evolution, wouldn't it? And I'm totally, like, if we found I would be like, wow. I mean, first I would be like, okay, let's see the methods. But I would also be like, wow, we really have some thinking to do. But that's not happened. And, I can ease your suspicion to the degree that you trust the methodology isn't malicious. But at the point where you're kind of like, I think that there might be something going on here that's like conspiratorial is like a harsh way of saying it, but it's conspiratorial. Like, I don't really know what to tell you, because like as far as I can tell, the methods are working as people have predicted that they would, and then it hashes out.
Yeah. Well, I wouldn't go as far as to say malicious or even conspiratorial. No way, no way, no way. But just a human error, human error. And so, like, we were trying to work on dating methods so that, I would be able to trust the dating methods when the dating as part of the evidence for human evolution, right?
Yes.
But now what I'm hearing you telling me is that, well, you can't actually, we're not actually testing the fossils, on that. We're testing the volcanic layers above and below.
Mm-hmm.
And so like there isn't really, we're not really dating so much the fossils by the layers that they're in. I mean, I don't know.
I would kind of create an analogy here, well, twofold. One, the same thing happened in Pompeii, though. We weren't dating, the structures in Pompeii. We were dating the ash, and using the ash to tell us that, this is the date that the eruption occurred. So I would propose that that's how we've always done it, and that's how we do it with any fossil, right? I mean, most creationists that I talk to are okay with relative ages, in the sense that it's like, if it radiometrically dates older, it was buried first, right? We can at least agree on that. And that's in geology called the law of superposition, right? So things that are lower, they tend to be older than the things that are above them. And I think that it would be akin to me when I was little kids, I would take little plastic dinosaurs and I'd stick them in cups of water, and then I'd put the water in the freezer and freeze it, and then get a cool, encased dinosaur in ice. But it's directly analogous to that. If a fossil is in a rock layer, right, that is encased on both sides by ash, right, it is no older than, it is no younger than the lower ash, and is no older than the upper ash. It can't be, unless you can. Unless you've got like quantum tunneling going on, or the rock has been potentially reworked. Now that is something that you could definitely have a point on. If you can show that these hominins have been reworked and that they have ended up in the wrong place in between these two layers, they're where they shouldn't be, that would be something. But that's why I was hoping to show, maybe I didn't show it well enough, but why I was hoping to show that the paper that comes out on the hominin is not all the work that's been done at the site. The paper that comes out on the hominin is like, hey, we found a new fossil, here's what it looks like, here's the diagnostic characteristics of it. It was found in this geologic layer in between tuff X and tuff Y, and you can find out more about it by going to this paper. And then you go to that paper, and it's a massive stratigraphic analysis of what is there and how we know that it is, right? I mean, I can't really say much more than that. I think like there isn't a logical issue with it. Like if you were to say to me, Erica, I think that it has been reworked, I'd be like, cool, yes, we can work with that. Let me try to show you that it hasn't been. But if you're like, I can't trust it if you can't date the direct fossil, we've never dated a fossil directly unless it was in the past 40,000 years.
Well, I mean, how about taking one of those fossils that's supposedly 2 million years old and testing it with radiocarbon?
It's filled with you can't test it for radiocarbon because there's no carbon in it. It's filled with rocks. Like when a rock fossilizes, and like this comes, I teach a biological anthropology class. This comes as a surprise to most people, but dinosaur bones aren't bones anymore. There's no original, or there's very little usually. There's the soft tissue stuff, which we could talk about, but there's very little original material in the vast majority of dinosaur fossils. It's undergone pair mineralization, which we've simulated this kind of thing in labs, and if I'm remembering correctly, we've seen certain early versions of it today, like things that fossilize relatively quickly because the conditions are just right. But the bottom line is, all that is inconsequential. When a bone permineralizes, you've got like the structure of the bone, and it's buried, right? Like let's say my fist is the structure of the bone buried. the bone will start to decompose as water and sediment seeps into the cavity and starts to replace the original bone. And so what you end up with is effectively a cast of the original material. When you end up with this soft tissue stuff, it's usually because certain matrices deep inside the bone weren't replaced. But 9 times out of 10, I don't know why I'm giving a stat to it. I don't know what it is for dinosaur bones. But most of this stuff is a rock. I mean, it's effectively a rock cast of a bone that was buried a long, long time ago. So if you were to try to radiometrically date it, first of all, you couldn't radiocarbon date it because there's no carbon in it. It's a rock. It'd be like radiocarbon dating a rock. But unless you were doing the soft tissue stuff, which is, we don't have any of that for hominins because the conditions are really bad for them. They're all deposited in these deserty savanna environments. It just dries these things out. But if you were to try to radiometrically date the rock, you're also in for a big problem because the infill is sedimentary, not igneous. It's not even metamorphic. So what you would be dating is the date that sedimentary rock formed in a volcano long before it ended up filling in the fossil. So you wouldn't get a date for the fossil, you would get a date for it would be like if I created a rubber cast of or a ceramic cast of my hand, and then I dated the ceramic cast. I'm not getting the date of my hand, I'm getting the date of the ceramics. Which is, again, why you're using those layers. And we, again, like I said, we do that for dinosaur bones as well. So that's what would happen if you tried to carbon date it. You couldn't, you would send it to the lab and they would be like, this isn't organic. There's no organics in here. Mary Schweitzer's work pulling organics from dinosaur bones. And I do think that she's got tissue there. In my opinion, there are people who disagree with me. I think that she does have actual tissue. That being said, Dr. Fuzrana, I've got his book on my shelf somewhere over here, has a very excellent book as to why the soft tissue in dinosaur bones is very problematic for a young age because of what's being preserved. Effectively, this soft tissue should be ubiquitous. It should be found in everything, and it shouldn't be the hardiest, most impossible to destroy if everything is quite young. It should be all kinds of soft tissue, because we see things get buried by water, and again, like I said, start to fossilize today, and there's still a ton of organics in there. So there would have to be something about the flood that I don't know what it would be, but it would have to cause paramineralization itself to happen faster and give the illusion of that the process is sped up. So that's what would happen if you tried to date the fossils themselves, as far as I'm aware.
Okay, so where do we go from here?
Well, I mean, I had a great time, but I also spent most of the time, I monologued at you for much more of it than I feel like you got to respond.
Oh, that was perfect. That's good. That's awesome.
I'm curious because I think do you think that we could agree, if we could agree on this one thing, I would feel comfortable moving forward with human evolution. Hold on, I have a stupid whiteboard here that I think might be able to better illustrate.
Go for it.
So I'm imagining I send you those papers and you kind of take a look at them yourself. And that would kind of be like our go-ahead to meet again maybe in like a month or so, whenever we felt like we wanted to or it was good for both of us. And you can kind of look at those dating methods. And if you could come to the conclusion, if you came to the conclusion that we could agree, there is at least a relative distance between these organisms, I think we could move on, because at that point I would want to show what I feel to be that there is a smooth, unbreakable gradient where you can't separate ape kinds from human kinds. And what I mean by that, I guess, is like if we have like ranges, right, of different dates, if we could agree that these ranges are even just relative, right, I think we could move on, because I feel confident in being able to make a case that even if they are relative, whether or not you're working with an old or a young Earth, they are indistinguishable as organisms on a gradient of change.
Yeah, and I feel confident. I feel comfortable agreeing to that.
Okay. Well, I think that that's good. I think what for our next conversation then, what I think I'll do is kind of compose something similar to what I did today, but I'd like to look in depth at some of the hominins that are, and what I want to do really is pick a few that are definitely they're definitely separated, right? They're not overlapping so much that it's like they're sister species. I want to pick things that could potentially be ancestor descendant, and I want to show you the traits that in human evolution we tend to focus on, and kind of show you the pictures of the fossils themselves. Like, what do we have? How have they been changed? Because that's a really important one. I hear a lot about the folks talking about Australopithecus Africanus, the Lucy specimen, that they don't like the way that it's been reconstructed, because some of these guys are found in a lot of pieces. So how do we know that the pieces that we find fit together correctly in the way that they do? I really think I can make a good case for that. And how do we know if a bone is found, not in articulation? And I think most people are surprised to know some of these are found in articulation with each other. Australopithecus Sediba is a classic example. I mean, the whole arm is basically one piece, and it's inches away from the rest of the rib cage, and I think that's pretty cool. But we have techniques as well to account for if I find a femur, 6 meters that way, how do I know that it's related to the hip that I have here? And a lot of that has to do with laser scanning the articular or joint surfaces to see if the wear matches up, like jigsaw puzzle pieces. And I think I can make a case for that too. So the last thing I really want to just touch on, because this one drives me crazy, is that some fossil specimens are a mix of Australopith or ape bones and human bones. I think I can make a case against that too. In the meantime, I'll send you the sources from today, and I'll start thinking about what I want to send you next time. Do you have any questions like for me that you want to ask me, or that you feel uncertain of? How'd you feel the talk went as a whole?
Well, I thought you did a very excellent job presenting, so I thought it went really well from that aspect of it. What?
You flatter me. I get paid to do this, so I hope I'm okay at giving a PowerPoint.
Yeah, and so I felt like you were answering a lot of my questions before I asked, and I was also very happy with that bones and Bible thing that you sent me. Yeah. I felt like it went well.
As a total side note, I'd be very curious to hear your thoughts. As like I said, I used to be a theistic evolutionist, and when I was, or evolutionary creationist, they call them two different things. But basically, just like I was of the opinion that the Earth is very ancient. God implemented evolution as a mechanism to keep life going. Whatever. And I really liked not just that book, The Bible of Rocks and Time, but also stuff that like John Walton put out, Joshua Swamidass. I liked Biologos, as most theistic evolutionists do. But that Bible, Rocks, and Time book doesn't talk about evolution at all. It's just talking about the age of the Earth. And the authors at the beginning are like, if you're here for evolution, leave, because we are not discussing it. But the whole first third of it, I think it's third, maybe fourth, is scripture. And I would be interested to hear the perspective of someone like yourself on if that's viable, because I know that for a lot of people, it's a scriptural thing first. And I can respect that. I mean, I know that that's an important thing, and I get it. I really do. But I'd be just as a total side note, if you do buy it on Amazon, if you ever get a hold of it, let me know what you think, because it's got some interesting. I thought they were quite good, but I also already agreed with them going in, so it was a little
right. Well, I will read it and see what I think, but I mean, there's only so much reading I can do if we're meeting next month, and actually, I'm not sure. If you sent me several papers, that might be hard for me to do in a month with all the other things that I'm doing.
Well, one, we don't have to do a month, and two, you don't have to. I mean, usually when I send papers, or when I read papers, if it's something that I'm writing a manuscript on myself, I'm taking notes. I'm like reading it like 8, 9 times, whatever, however, because I really want to make sure I get the concept. But if I'm reading something that's outside of my general field, I tend to focus on how they did it, like the methodology, and usually the discussion and the conclusion. And if you can get those two things, then you can kind of skip the intro. Usually don't have to read. I mean, the abstract is just going to tell you what the conclusion tells you anyways. But you'll know how they did it. You'll know what the results that. So it kind of shaves off some time. But right. I don't think I don't really think I need to send you like papers on the hominins, because I mean, if we do talk in a month or more, if you need more time, I think it's been easier for me in the past to have someone just tell me, like, because there's a lot of anatomy. It's like, okay, this is what you're looking at is the femur articulating, with the acetabulum. Look at the and then you show them side by side. Just look at them. Because I mean, and I try to do that on my channel, but like, it really irritates me when I see, people talking about human evolution. It's always, like, not always, but a lot of times it's cartoons. And it's like, okay, I appreciate the cartoon drawing that you did to show the comparison, but show me the fossil itself, right?
Right.
That's what matters, is what does the thing look like? And what does it look like compared to the human? So that's what I mean, it's probably just going to be a bunch of, like, the papers that I sent you would be like, what's laser scanning joint articular surfaces? How do we tell, like a paper on being able to match individuals with close remains, or a paper on I don't know, the burial position of something, if it's important, right? Because it's unusual. I don't think I would send you very much.
Okay, cool. Yeah, I mean, that sounds like fun. It sounds like a good project. I mean, how did you feel like the talk went?
Yeah, I think it went well. I mean, of course, I do YouTube and I teach, so I love to hear myself talk. It's just, I have to. And my voice is very nasally and high pitched, so I actually do get sick of hearing myself. I think it went well. I wanted to get across. I hope you kind of understand better where I'm coming from, and like why I feel that this is robust, even if you don't walk away feeling that way. Right. My goal is always like, I want you to feel that I've given this some thought, I guess, that I'm not just going in willy-nilly and like trusting, the people who say the things that they say. It's like I see a hominin and then I'm like, okay, I see the thing, let's go back and look at how it was dated. And this all started because, like I told you in our email exchange, I used to get coffee with a young Earth creationist friend, and it wasn't until then that I realized how little I knew about the things that I thought I knew, right? Like, I would say things like, okay, well, it's radiometrically dated to be old. And he's like, he'd hit me with like okay, well, how do you know that the rates are constant, right? Like, how do you know that it's all parent material at the beginning, right? How do you know the things that you think that you know? And I kind of got really into it. Like, now, when it's really changed my way of thinking, where it's like, when I see a thing, I'm like, oh, interesting. How do we know that? What's backing it up? And unfortunately, especially in today's day and age, it will lead you down a lot of holes where you go and look at the study and you find out the sample size is tiny, or the methods were inappropriate, or, their conclusion was wacky. And from then, next time you see someone cite it, you can be like, did you read it? Because I read it.
Yeah.
I think that's a useful skill.
Do you find that ever with your perspective? Like, do you find, problems in methodology problems and conclusions with what you believe now?
I do. I absolutely do. I hope that it's that way with every field. I think that the ability to call people out when their methods are bad, or their stats are bad, or their analysis is bad, is it's one of the greatest. I said mutability is one of the greatest strengths of sciences, but peer review is the other one. It's the ability of your peers being able to say, wait a second, that thing that you just said, that's bonkers, right? A classic example is Bernard Wood. He discovered Hominoleti, right? Hominoleti is this critter that lived in South Africa. It's very recent. 200,000, 250,000 years ago is what it's dated to, which means that from a secular perspective, it lived alongside humans and Neanderthals and Denisovans and Homo floresiensis, all these other guys. but it's really primitive. Its face is strange, and its whole lower body is like pretty par for the course for a biped, but the upper body is very weird. It's not surprising that it's down in South Africa, but when Lee first discovered it, his idea was that it's like, ooh, this might be an ancestor of Homo sapiens, right? And he seemed very eager to make that case. But when you go and you look at what he's actually presented, he was not very good at it, right? There were a lot of apomorphies, or like unique derived characteristics applied that Homo naledi has that do not work. If it would have to lose those traits first and then gain other traits that would make it more similar to Homo sapiens, and then you get to the dating and you're like, wait a second, you think it's ancestral but it's 200,000 250,000 years ago? That's not going to work. And it's for that reason that he was annihilated in the press by other paleoanthropologists. I mean, you can find what he published. I think it's in eLife. But no paleoanthropologist that I've interacted with, and I've interacted with a lot of them, thinks that was a very good assessment of the fossil. Now, that doesn't mean that the fossil's fake. It doesn't mean that it's not a cool fossil. It's a really cool fossil. He found so many of these guys, and they're all found in Rising Star Cave. It's very strange, like how they end up there. Were they buried there? Was it intentional burial? Was it geologic? Did they end up there because they were swept by a river? A lot of unanswered questions. And speculation is another thing that drives me crazy. Like, I hate when people in paleoanthropology are like, oh, it's clear that this hominin buried its dead. It's like, okay, how is it clear? Tell me how you think it's clear. What is it that makes it clear to you? And some people knock it out of the park when they present it. I mean, there's hominins that are buried with the pollen remains of flowers all around them. It's like, okay, that's probably intentional burial. Or they're posed in a certain position, which is probably intentional burial. But then you find some and it's like there's gnaw marks on them, and it's like, okay, that was not intentional. So I do find these problems in my own field. And when I, dare to venture out of my own field, it's harder. I mean, I find it in primatology sometimes too, where it's like, they'll document some really interesting behavior, but their sample size is too small to be able to apply it to the species as a whole. So I do. But I hope that perhaps it gives you a little bit more confidence in conversing with me as a person that is something that I find and I look out for. But as a last thing on that, there are certain aspects that aren't up to interpretation that you can't screw up. And I think, or you can screw it up, but you can't screw up the interpretation of it, right? Like if the dating is one thing, you can't look at that, publish that number and make an argument that it's not that number. You know what I mean? It's like, dating methods tend to be, if you actually have the dating methods, then once it's there, it's usually pretty solid. Same thing with morphology. Like if you find a solid skull or a solid femur or something like that, you're gonna really have to present a good case that a valgus knee, so a knee that bears the weight underneath the body, belongs to a quadruped. That's biomechanically not possible. But no one ever makes those arguments. It's usually other stuff that I'm like, it's the speculative stuff. And the dinosaur people are rife with this too, or so I hear from my Mesozoic research friends. Okay, sweet. I've kept you for almost 2 hours. So this has been very fun to me. I really enjoyed it, and thank you for taking the time. And I hope that I hope that this was